Hey everyone, in this video we're going to be talking about engine classifications as part of a short video series on IC engines. And we're going to be looking at different types of classifications of engines to be able to differentiate between engines. This is very important in order to get a better understanding of how we can classify engines in the future. So the first way in which we classify engines as design engineers and internal combustion engineers is by its ignition. And there's two main ways that we look at ignition. One of them is called spark ignited engines or spark ignition engines. And this is abbreviated as SI usually. And in this case, you usually have a spark plug with a high voltage, and the spark plug is what creates a flame in order to create some power. So we use chemical energy and we convert that chemical energy into thermal energy, which then increases the pressure and pushes the piston down. Now, the other type of engine that we have is compression ignition, and that would be classified with a CI abbreviation. And this is a different type of combustion where we use high pressure in order to ignite the fuel and create some power. So we use a high pressure combustion as opposed to a spark plug. The next type of classification that we can use is two-stroke versus four-stroke. And this is when an engine uses either two strokes to complete a cycle or four strokes to complete a cycle. A stroke is when the engine or the piston moves from bottom dead center to top dead center or vice versa. But we'll go into more detail on this in a future video on four-stroke as well as two-stroke. The next type of classification that we want to talk about is looking at different types of valve location. And there's many different engines that have many different valve locations and valve designs. And pretty much all engines are unique in their valve design and valve passages. So valves are used to bring air into the engine and out of the engine, and we use ports in order to do so. So valves are the things that close and open in order to let the air into the engine and out of the engine. So here you have a drawing of a piston cylinder assembly with a combustion chamber above top dead center. You also have bottom dead center shown there, and you have a piston in green shown as if it were at top dead center. And you can see that the piston moves up and down between bottom dead center and top dead center. Now, this type of design has ports at the top usually, so you can see those ports at the top, and you have valves within those ports that open and close to let the air in and out based on the cycle. Now, we will discuss how the cycle works and how the intake port and exhaust port works, but here we're just labeling different things. This design is called an overhead valve design, and this is because you can see that the valves are overhead or over the combustion chamber. So when this type of design is done, we have actually a split engine block. So we have an engine block at the bottom and then a cylinder head at the top. So that's why we call them overhead valves. And the valves are directly placed in the head, which is the part in metal at the top. But we'll go over this in future videos in much more detail. Now, this is a typical design that's used nowadays and is the most common design. Now, let's try and think of other designs or other variants of design. So one way to differentiate the design that we have is to look at two valves versus four valve design, and we'll get back to that in a second. But the other type of design, and there are many, many different designs, is the use of a T-head. So a T-head is an older design, and it's just an example of an older design that used to be used for space savings, so it's very good for space savings. The only problem is that the fluid mechanics and the fluid dynamics are not very good, so the fluids have to turn around a corner, which makes it a lot harder to get good flow and not a lot of losses in pressure. So it's not a very good design for nowadays, because nowadays we can design some very good engines with overhead valves, but this was used more in the 60s and 70s when engines were really becoming commonplace. So you can see that the valves are upside down and moving up and down to let the intake air go in. So I'll draw now how the intake air would go in. So you can see the blue lines being drawn with the intake air coming in, and then the exhaust would come out the other side essentially. So this design Advantages are that it takes less space at the top, so you can have very short engine bays. The one disadvantage is that the flow has to go around a lot of different corners. Now, I want to get back to 2 versus 4 valves and look at the top view of a 2-valve engine versus a 4-valve engine. Now, there's many different numbers that you can use. You can use 5 valves, 6 valves, 7 valves, however many you want. But a 2-valve engine will usually have 1 intake and 1 exhaust. A 4-valve engine will usually have 2 intakes and 2 exhausts. And as you can see, the 4-valve engine has a better use of the area. You can get away with using more area for the intake and exhaust. Now, one thing that the advantage of a 2-valve engine has is that you can use two spark plugs if you want to, whereas with a 4-valve engine, it's a little bit harder to use four spark plugs, so you usually use only 2 spark plugs. Now, the next type of category is looking at different types of engines as a whole. And the most common type of engine is reciprocating, which is basically means the engine goes up and down. So that's a typical piston cylinder engine. Another type of engine is called a rotary engine. And what the rotary engine does is it actually has 2 or 3 chambers rotating around a center axis. And this is a completely different design that has been used by Mazda on their RX-7 engines mostly and RX-8 engines, but has fallen out of fashion a little bit because of some difficulties with sealing the chambers when you have rotating chambers. So the next type of engine that we want to divide by is reciprocating configurations. And so most common engine is a reciprocating engine, therefore it makes sense to separate the different types of reciprocating configurations that we can have. Now, these reciprocating configurations you probably already heard of, but one of them is a single cylinder. So single cylinder is a very simple engine. It's usually used on small motorbikes or small vehicles where you only need 1 cylinder to power and you don't have much space and you don't need much power. But usually you'll line these cylinders up in, for example, an inline 4 engine. So the next option is an inline 4 engine where you would essentially have 4 of these single cylinder engines put together into one engine essentially. And there's some balancing questions with that, and there's a lot of different parameters of design, but this is just an introductory video really. The next type that you all know is a V-type engine. So a V-type engine has a V-shaped design, and there's many different designs associated with these. So you can have a V6, a V8, a V10, a V12, many different ones. But essentially, you would take the inline 4 and you would double the inline 4 and put them at a certain angle. So you'd have 4 cylinders pointing towards the left and 4 cylinders pointing towards the right in a V shape. The next type of engine is called a flat boxer engine, and usually that's at essentially the equivalent of a 180-degree V, which you would essentially have opposing cylinders, and you usually have 2 and 2. So these engines are designed a lot by Subaru. Subaru has a lot of different types of boxer engines, which is usually called a 4-cylinder boxer or a 4-cylinder flat engine. Porsche also does flat 6s, so we also have those. Now the last type of engine is a little bit of a quirky engine. It's called a W12, and some people have some misconceptions about that. But a W engine is with 3 banks of cylinders with 4, 4, and 4 as shown here. The next type of classification I want to go through is looking at the 3 main types of air intake methodologies. And the first one is just to use a naturally aspirated engine, which is what most engines have nowadays. Although turbocharged engines are taking over a lot of the market for its benefits in efficiency of combustion and efficiency of just thermal efficiency in general. So naturally aspirated engine means the pressure in the cylinder is usually less than pressure atmosphere. So we have atmospheric air outside, and we use the piston going down to suction some air into the cylinder, and usually that pressure in the cylinder is lower. So we don't have a very high density of air, and that means we're limited in the amount of combustion we can have and the amount of power we can create. Now, a solution to that is to use a supercharger or a supercharged engine, which is also called a compressor, and it works in the same way as a compressor that you might have seen in a thermodynamics class. And what this supercharger does is you add essentially a supercharger or a compressor on the intake, and you compress the air. So from pressure atmospheric, you maybe have 1 atmosphere coming in, and that 1 atmosphere coming in would be increased to a 2 atmosphere level. So the pressure in the cylinder would be a lot higher, which means the density of the air in the cylinder would be a lot higher, and therefore you can have more power every cycle because you can add more fuel as well. It's the same concept with a turbocharger, except a turbocharger is designed kind of differently. So a supercharger takes its energy mechanically, so it compresses the air mechanically, so you have to have a mechanical system compressing the air. Whereas with a turbocharger, what you do is you use a turbine in the exhaust to be rotated by the exhaust gases passing through. And this turbine, denoted by T here, and C in a compressor, they're connected together by a shaft. So the turbine is rotated by the exhaust. The exhaust rotates this turbine to, for example, 50,000 RPM. And then this 50,000 RPM then powers a compressor in order to compress the air. So the nice thing is that we're using the exhaust gases, or the exhaust powers a turbine which compresses the intake air. And that is very good because the exhaust would be otherwise a wasted energy, essentially. So we're reusing wasted energy as opposed to having a mechanical system powering the compressor, which helps a lot in terms of efficiency and is really the future way to go when we design very efficient combustion engines. Now, the next categorization that we have to look at, that we haven't really looked at yet, and that is extremely important, is when we talk about an engine, we have to talk about the different fuels we can use in an engine. So diesel is typically used in trucks and big semi-trucks as well as buses. Gasoline is used in smaller passenger vehicles such as cars. Then alcohol is also a very popular fuel, and the oxygen is in the fuel, which actually helps with combustion. So that's a very good fuel for combustion. The only problem is that there are some drawbacks in terms of efficiency. The next fuel type is hydrogen, which actually is a very interesting fuel in the sense that if you burn hydrogen, the only byproduct is water. And this is great because it actually doesn't pollute anything. So by combusting hydrogen and oxygen together, you would only create water, which is a great byproduct to have. We wouldn't create carbon dioxide as well. However, hydrogen is very unstable and it's very hard to combust correctly. So it hasn't been done in an internal combustion engine as of yet for full commercialization. The other two are natural gas and LPG, which is liquid propane gas. Those are also some alternatives, especially for different types of engines, not necessarily on vehicles. Now that we've covered the fuels, let's look at the different types of fuel injection we can have on an engine. So different types of fuel injection are the following. We can have a carburetor injected engine, which is an older style of injection that we used for fuel. So that's when you mix fuel directly with the airflow and you use the speed of the air to kind of mix the fuel. A second type is port fuel injection, which is more modern type of fuel injection, and then direct injection into your cylinder. So using the same diagram as before, I'm going to show you where carburetor would be. So carburetor is where A is noted. Then port fuel injection happens pretty late into the intake port, right before the cylinder, right before the valve, and then C, the direct injection happens directly in the cylinder. Now, all three have different advantages and disadvantages, which we'll look at at a later stage in this video series. However, you can think of B being the most common, C is growing and becoming more common, and A used to be more in the past. The last categorization that we want to look at is the types of cooling that you can have on an engine. So there's really two types of cooling. One is to air cool, and the other one is to liquid cool the engine. Now, most engines are liquid cooled nowadays because it's a lot more efficient. So they use the air with a heat exchanger to cool a liquid that then runs through your engine, but there are still some air-cooled engines as well. In the next video, we're going to be looking at how four-stroke cycles work, and we're going to do an in-depth analysis of a four-stroke cycle and go step by step through a four-stroke cycle to really understand what is happening. This overview will then allow us to go into depth in the four strokes and really dig deep into the engineering analysis of every single step in a cycle of an internal combustion engine. If you have any questions or suggestions, please leave them in the comment section down below. And if not, we'll see you in the next video.